23rd of September 2023. Today we have a very important and interesting topic in present scenario related with photovoltaic metrology. The measurement in photovoltaic cells, or many times we are aware about the solar cells. We have with us Professor Dr. Sushil Kumar. He's a chief scientist G from National Physical Laboratory, India. Sir, we are pleased to have with you, and we are thankful to you. You have accepted our request to deliver a talk on this very important topic, which is related with the common man, industries, and many new R&D people or the industries who wish to do R&D in this field. It will be a very useful workshop today. We have with us our Honorable Shri B.N. Dixit, Director, former Director Legal Metrology. Sir, I would like to request you to kindly speak 2 words on this new subject, photovoltaic metrology. How the metrology will impact this field. Shri Dixit, sir, please.
Okay, this is the new topics, but it is some way the part of the legal metrology also. So, Sri Ashutosh Agarwal, Deputy Director RSL, Ahmedabad, are organizing various such topics every Saturday for the peoples and scientists and students and those who are interested to participate in such seminars. I think these seminars will be helpful to all the peoples, and Dr. Scientist from NPL, his presentation will be very fruitful to us, and people will know about the solar systems and about cells and how it is working and all these very things. Thank you. आप proceed करिए.
Thank you very much, sir. Thank you. Thank you very much for your kind words. Certainly, sir, we are trying our best to take these topics which are not very common to all the participants who are actually interested. Sir, we have with us Dr. Sushil Kumar. He is a chief scientist and honorary professor of physical sciences at Academy of Scientific and Innovative Research. He received his PhD degree in electronics from IIT BHU, Varanasi, and BSc Honors and MSc Physics with specialization in electronics from BHU. So, sir, he is from basic your Varanasi city. He has completed his
also from
education
BHU.
from Varanasi.
Nice to welcome Dr. Sushil Kumar. I am also from BHU.
Sir, he was a visiting fellow at CNRS Paris, France for 1 year. He has significantly contributed in the area of solar cells, plasma, conducted thin film materials and coatings. Presently, he is heading the photovoltaic metrology section of CSIR NPL towards the development of primary and secondary standards for solar cells, development of waste management technologies such as recycling of waste solar modules, plastic waste and other electronic waste for their social application, silicon-based heterojunction solar cells, covering basic and applied research spanning from wafer-based silicon photovoltaic technology, thin film to latest concepts such as organic and perovskites, organic, inorganic, heterostructures-based solar cells. So he has a lot of experience, a lot of research papers. He is already linked with different organizations, not only in India, but at the international level. Sir, thank you very much. I would like to request Professor Sushil Kumar to kindly take over and enlighten us with his knowledge and experience to all our participants. Dr. Sushil Kumar, please, sir.
Thank you very much, Dr. Ashutosh Agarwal and Dr. Dixit, for inviting me and giving this forum to deliver a talk. As asked for photovoltaic metrology, so this is the, let me open my slide and kindly confirm it is visible.
Yes, sir, it is visible.
Okay, that's nice. So, as photovoltaic metrology,
sir, you can put it in the presentation mode. I'm sorry, sir, you can put it in the presentation mode, please.
Pardon?
You kindly put it in the presentation mode.
Yeah, it is in presentation mode. maybe again I have to see. Actually, I'm also getting less wires from your side. I don't know where is the
So maybe your
problem.
signal may be breaking.
In the
Your
in
Yeah.
the
signal may
blue
be.
corner, in the right side blue corner. Yes.
Yes.
Ye-
No, again, click it. It was not clicked.
Um, just a minute. Again, I'll try to share with. Yeah, now confirm. Is it full screen?
No, sir. No, sir. Please click on full screen mode, sir.
Hello.
Sir, screen is not in full screen mode.
You may continue, sir. No problem.
No, no, no. Let me because I understand it has to be on full screen. Then only it will be clear to see for everyone. Uh, Now,
It is better, sir. Please continue.
okay. Thank you. So as I will talk about 3M, I say materials, module, and the measurement. All three are important in any photovoltaic devices, starting from the material, making of the cell and the module, and its measurement at each level. So this is what I have chosen the topic under this photovoltaic metrology. And I always used to show this figure. It is to my heart. You know, this is a picture taken one of the glacier in Argentina in 1928. You see, completely snow covered, and now it is with the lake. It's all melted, and we all understand why this is happening and how it is important to talk about the photovoltaic and the renewable energy. If I show you this data, this is about the average temperature increase of the earth, and as well as the increase in the carbon dioxide in the environment. So these are the two contributions which is making a problem to all of us, and also the use of fossil fuel. And in the starting of 20th century, it's all started, and definitely it will be over soon. So these two are contributing to our environment, and this is the mitigation. That is why everyone is concerned. So two major problems: shortage of energy and the climate change. So for the shortage of energy and the climate change, where the solar cell plays a major role for the both the things. And the fossil fuel, we know that it is limited worldwide. Energy demand is growing, and we need to reduce the carbon dioxide emission. Also, we need to reduce so that we can have a better environment for our future generation. So considering these all aspects, there is a paradigm shift. Uh, we can understand, particularly in our government. Yes, this is a lot of initiative has been taken under national mission program, and worldwide also many countries they are focusing towards this solution for our climate change affecting CO2 gas, that is because of the CO2 gas. So efficient use of energy, that is the one thing, how efficiently we can use. Even in the solar cell, if I say the module, the efficiency is the requirement. Of course, the cost reduction is also the factor so that it can be widely used. And its measurement at each aspect it becomes important. I will talk about that. The renewable energy sources, under that the solar energy. So this is the slide. There those who are not exactly in the field, basically for the beginners, sometimes they get confused with the two technology of solar tech. That is, we can understand that the one is photovoltaic technology, other is the thermal based technology. In the photovoltaic technology, we take the photon for generation of electricity, and it is possible with a semiconductor material. Essentially, you need to use the solar radiation, having a proper tuning of the radiation depending upon your the material. I'll cover about that. And the second technology, the thermal technology, this is basically the heat part in the solar radiation that is being used to heat the some medium, and through that medium, basically, if that medium is
I'm sorry,
heated,
sir.
let's say,
I'm sorry, sir. I'm
hello.
sorry. I'm sorry, sir. We are only able to see the first slide, which is just your name. We have not. The slide has not changed.
Really? Oh.
Yeah, now it is changed. We are looking towards
Actually,
solar technology.
it seems that when I am going to full mode presentation, the slide is not changing, right?
No issue. Now it is okay. Please continue in the same way.
Same way.
Yeah.
Okay.
No problem. Now
Uh,
it is
so let
paradigm
Yeah.
shift.
So actually, this was my second slide. I talked about the increase of temperature and CO2. Here about the use of fossil fuel, and both are contributing to a major problem for the climate, and this is what it is needed, and there is a paradigmic shift in a thought at the government level, of course. So which is what I am talking about related to two technology, the photovoltaic and the solar thermal. In the solar thermal, uh, just where I stopped before this, the basically the medium gets heated, and that medium maybe the water and the steam generated, and that steam can be used for running of a turbine and electricity production. So basically these two are different technology. Particularly in the photovoltaic, the first technology, the solar cell essentially incorporated there. That's measurement is important. So how this photovoltaic system is basically the smallest constituent, it is a cell, the solar cell, and that comes into a module. When module is made, basically the connection of cells in series or parallel depending upon our requirement, what specification we want of the power in terms of its current and the voltage, and then these modules connected to form the series. And this can be a standalone system, rooftop system, or in the solar park with the grid connected. So this all way is possible to have a photovoltaic. Now, the solar cell, as I mentioned, the initially this has to be measured properly. Its fabrication process is measuring so that you can have a better efficiency. Basically, the technology has to have so that you can have a good efficiency, and how efficiencies parameters you are measuring, that is the important thing. In the module, yes, normally we measure the power in terms of its current and the voltage, then it go into the solar array and the solar system. So these are the performance parameters which needs to be measured. And the solar cell, how they are incorporated in the module. uh, so the solar cell is the essential more is the silicon. There are other materials also involved. I will talk about that also because you have given me 2 hours time, so I hope can cover all these things. So just to start with the silicon solar cell, the silicon is there, and in the PN junction form, the junctions are framed. Then you have a anti-reflection coating, the metal grid at the top, at the bottom you have also a metal contact, and they are connected with a copper strip in series or the parallel depending upon, as I mentioned, the power is required in terms of its current and voltage for different application, or the where what kind of a load you have, and that goes into the module like here it is shown here. And over this cell, you can have a 2 layer of ethyl vinyl acetate. Basically, it is an encapsulant that is a polymeric layer, and over there you have a tempered glass. The glass is being used, and at the bottom also there is a polymer that is called PT, PET or PF based polymer sheet, and all this get framed with the aluminum frame so that you can have a mechanical support from outside. So all these are stacked in the cell. Normally, whatever you see at the installation places or the rooftop or wherever in the field, it is the module we see. And normal life of these modules is 25 years. And with time, it's degrade. So there are standards at what rate it is permitted for degradation. If it's degrade to 20% means it should have a 80% operational power from the beginning to end, so that it can call as a live module. Otherwise, it will be declared as a discarded module. There are standards for it. So this is how a module is made, consisting of solar cells. And if I talk about the choice of solar cell material, the kind of solar cell technology are there. The solar cell is also the first generation, second generation, and the third generation solar cell. About 95% of the market or the installation site you see, the cells are of silicon, that is the wafer based cell. They are having monocrystalline or the multicrystalline. About 2-3 years ago, it was maximum of multicrystalline silicon, but now with the change in the technology and the cost effectiveness, most of the companies have adopted monocrystalline cells. They have a better crystal structure and lesser defects. That way, it is possible to have the better efficiency. So these are called the first generation solar cells, and having more, this is what in number it is installed, about the 95%. And for this module, it has a standard IEC EN 6.2515. There is another cell that comes into the second generation cell, the thin film solar cell, the CIGS, CGS, CDTE, gallium arsenide based. Gallium arsenide is mainly for the space application, because it's not that cost effective material. Material is very costly, and the process is also very costly, because these are made with a multi-junction solar cell, having quite higher efficiency. But the CDT, it's quite popular among the thin film, and about 5% market it has captured. Earlier, the amorphous silicon solar cell was also very popular till 2010 or so. Whatever the NICE application you see in the calculator and other thing, it's all amorphous silicon solar cells. This also went into the module, but with the advancement in the technology and particularly I say it is a scale up that made the crystalline silicon widely used after 2010 with the huge mark production of when the Chinese solar module producers. So that made a complete change in a scenario in the installation, and mostly the crystalline silicon solar cell were installed during the last 10 years, and it is expected in also in coming years, most of the modules will be of the silicon solar cell. And there are emerging technology also, the third generation solar cell, dye-synthesized solar cell, organic solar cell, perovskite or quantum dots, various nanostructure. I have not listed all, but there are many materials dependent. But they mostly, I can say all of them are at the lab scale only, except few for dye-synthesized and organic. People have tried at the pilot scale, but yet it is not commercialized. So this is called the third generation. Sometimes people say third and fourth, some with the new idea. So that is what it is found in the literature. So as for thin film solar cell, there is a standard that is called IEC EN 61646. But for organic solar cell or other this third generation solar cell, as such, there is no standard available. But in NPL, we have made a protocol. I will present in front of you few things about this emerging photovoltaic also, how one should measure in lab at least, so that uniformity across the globe will follow, so that whatever efficiency we say, it should be measured same at the different other labs also globally. So moving further, more or less the same things I have shown in a different way, so that you can have a complete picture of it, photovoltaic technology. So ultimately, what I say, the photovoltaic technology, it's all depend on the kind of material of your choice, means which material you are choosing. It's all material dependent base. The silicon, of course, is a widely, but there are other different materials, as I mentioned. So this is another slide which says about the various records made, how efficiency progressed with time. Here data, it is shown by the NREL, it's Apex Laboratory of US. They keep the record of all champion solar cell, like we have in Olympics, I can say, or some world championships. Various athletes made a record, like in different racing and other events. Similarly, NRL make a record of all the different kind of solar cells, but they have a minimum size requirement. At least cell size should be 1 centimeter by 1 centimeter. Then they only measure and keep a record of it. So with different color, you see different kind of cells presented here. The starting from multi-junction and others, crystalline silicon, emerging PV, thin film technology, whatever the class of materials I mentioned, it's all various cell efficiency indicated. The data points here for all the cells, it is whenever there is a change in the efficiency, improvement in the efficiency, that comes into this graph. So for 2022, it's latest one, it's all here, and these are the different labs. So as for the commercialized cell, as I mentioned, the first generation and the second generation, they are only the commercial solar cells, solar module panels are available. And like monocrystalline silicon and the polycrystalline silicon in the first generation, in the monocrystalline, the efficiency from 20 to 22%, it's all available. And it is because of the purity of the silicon that makes more efficiency in this. Polycrystalline 18 to 20%. In amorphous silicon, it is a thin film solar cell. The growth process is entirely different for this. In the monocrystalline or the polycrystalline, basically it comes from the sand, the normal sand, that is the quartz, it's the SiO2. And the process is there. You need to heat it up around more than its melting temperature, 1800 to 2000 degrees Celsius under the carbon atmosphere. And so that you can have a metallurgical grade silicon, and metallurgical grade silicons are used in many other applications, in various alloy formation, in rubber industries, they all use. So hardly 10% comes in semiconductor, that's include your microelectronics and the solar cell. And so in the after this metallurgical grade silicon, further process is needed that go with the Siemens process. I'm not presenting in detail, just briefly I'm making things here. And then CZ process, FZ process, all processes are there so that you can have a pure silicon. For silicon, for solar cell, you need at least 5N. For microelectronics, 9N purity is needed. So this is how this silicon are made. The ingot that is called ingots. In the case of amorphous silicon, it is not in that way it is produced. It is produced in a vacuum chamber in the thin film on some supporting surface. Like on the glass, you have to grow the amorphous silicon layer using the plasma. So here the SiH4, that is the gas, is being used so that you can have a silicon thin film. The advantage of silicon thin film is that it is a very thin cell layer is needed, hardly 1 micron or so, but they are in the bulk based silicon, that is monocrystalline or polycrystalline silicon, there 200 micron is needed. But since efficiency is not getting boosting in this, so it is somehow it has lost its market share. But in around 2010 and 11, it was 10% market share was there. Similarly, CIGS, that is copper, indium, gallium cyanide, it gives 15 to 17%. This is also a thin film process deposited under vacuum, and CDT in the same way, it's a vacuum based process. 14 to 16% efficiency is possible. Some companies now is First Solar, that is the important one of the company, it's doing quite a good thing, and efficiency will come up. So basically the CDT is the technology which is giving somewhat competition to silicon based technology. These are various materials involved, and they are in these different technologies. If you see, normally always it is there, in the lab the efficiency comes more, but when it goes into the module there is a loss of efficiency. Some recent data is given here, like for silicon, monocrystalline and the multicrystalline silicon, 26.7% is the highest efficiency as of now for the silicon, and for module when made it comes down to 24.4, but in the module there is a loss, aperture loss, and also some contact loss comes because of that it happens. In the multicrystalline 24.4, similarly here also you see some loss is there. Similarly in the CIGS cell, or even in the CBT and the perovskite, this is a newer technology. It is for very small size module given, and the cell 1 centimeter square. It is in the lab only. So 23, if it comes here, there's a big loss there. So this is how it is from cell to module. There is a loss of efficiency. And as for the progress in the technology, in the commercial cell efficiency, starting from 1960 to till now, if you say earlier it was all unpassivated solar cell, I mean to say it was not properly, basically whenever the light is get absorbed, electron hole pairs created and they get lost in the recombination process, the passivation at the surface is needed. So earlier that technology was not there, so efficiency was poorer, but once people have started learning about the passivation, during 1980s or so, then the passivated emitter solar cells came in, and then PERC solar cell. This is also the passive emitter rear contact, the back contact, because maximum loss comes in the back contact. And then other advancement in the technology came, the top phone and other. Now people have started working in the tandem solar cell, though it is not in the market, but in the lab scale it is presented. And this line is about 29%. It is the physical limit for silicon solar cell, the 29%. And with a single cell, it is not possible to go beyond that. So that people have started using some other material along with the silicon. So that it is called a one cell over other cell, the stack of cells, and so that efficiency can be improved. So starting from aluminum BSF, the back surface field, to today's technology, the PERC, that is passivated emitter rear contact cells. This is how the progress has been made. And the technology also changes with time, and this is basically the data given for the various market share of different technology with time. You see, before that I'll like to show you this. This is how the conventional solar cell, as I was mentioning, the BSF, the back surface field, essentially it is a silicon material, and over that junction is formed by doping from the top side. So you can have a junction there, so PN junctions. It's a solar cell is a semiconductor device with basically the PN junction that makes the separation of carrier when light get absorbed there. So light absorbed in the bulk of the material, and then charge gets separated at the junction. But to avoid to have a anti-reflection coating means more absorption you should have there. Mean to minimize the reflection losses, texturing is performed and the surface area also increase so that you can have a more absorption there. Contacts are made, the top contact and the bottom contact. With the screen printing, silver is used and the back it's screen printed aluminum is used. So here data is shown for from aluminum BSF, like it is, if you see this blue line and it is changing with the red light with line with the time. This is because of the change in the technology. So continuation with that, if you see from starting again from there 2021 to 22 and 23 is all now different technology. Now it's a per solar cell and it is expected different technology like top on or the heterojunction solar cell will come. It's always evolving, and in the measurement one has to take care of these things also that I'll show you. Just going with some basic things because I understand maybe some freshers or the students might have joined. So as I mentioned, since I'm not running the full mode slide, so it was under animation. But anyway, the complete picture is here. You can understand. So you have a two layer, the P and N junction, and when sunlight, the sun rays falls on it, it gets absorbed and your electron hole pair created, and the electron and holes get separated because of this depletion zone. Positive and negative charges and charge get separated, and you can have a electric current in the outer circuit, and whatever load you have, you can get the electricity there. So this is how the solar cell works. And so what is the ideal condition? So this is the normal solar cell. If I say, so we want a complete absorption of light, 100%. This is what our wish, but it never takes place. And complete absorption and the electron hole pair creation without any loss, and its collection at the contact. This is what the ideal conduction means. There should be a ohmic contact, perfect ohmic contact, so that you can get the complete current, the electron out of the solar cell. And this is what we always desire, and depending on that, technology gets evolved. This is a famous paper where the maximum limit of silicon solar cell is given 29.4% theoretical limit, but in the tandem cell now it is, has crossed, and you can see the best cell as of date now 26.7% is already made. So we are very close to theoretical limit of silicon solar cell. 90% is, so it's a great achievement over the year, and now people started working towards higher efficiency, more than 30% efficiency one can realize, but it is not possible with only silicon, as I in the beginning also I mentioned. With some use of other layers, it's possible. So this curve is basically it's a efficiency curve with the band gap of the material. So that is what here comes the material importance. What kind of a material? Because the material structure and its bonding structure gives the band gap, and the band gap basically that decides, yes, how much your light is going to absorb there. You know that as for the band gap, your light will go there, and above that it will close to that it will absorb, above that it will waste as a heat, and lower than band gap all energy will pass through it. So band gap is a critical parameter which decides the efficiency of any solar cell. So when we go for measurement of a solar cell, so you have a two contact there, the top contact and the bottom contact, and just you need to take the IV curve of that. So it means you have to illuminate the light. You know the standard illumination light is solar energy and A 1.5. I'll tell you about that. What is that? And when that light falls on a solar cell, a current produced. So with as a function of voltage, one has to measure the IV curve. That is what it is the requirement. So when there is no light, this is this white line. This is your curve. That is the dark current. This is simple IV characteristic of a PN junction. Under dark, there is no light. But when light falls on it, there is an enhancement in the current. The more electron is there, and because of that, you have a photo-generated current, and this curve shift over here, and this way you get the IV curve. Okay, and this this area covered in this, that decides the your what is the efficiency and what is power in that device. So this is how one go with the measurement. Further, I'll elaborating more. If you see this curve, just the in the fourth quadrant it was shown. Why it was fourth quadrant? Because you are taking out the energy from a device. Your device is a PN junction. From that you are taking an energy. That is why it is a your negative current and the positive voltage. What it was given here in the fourth quadrant. Now the same for the simplicity. It is shown in the first quadrant. I mean to say, and as a voltage versus current, a typical example, if I say 10% efficiency, what does it mean? It means, yes, you have allow a light to fall, and it it is a power of 100. So out of that, only you are getting 10% power, right? It means if whatever the energy conversion is there, it is the 10%. So this is represented in this IV curve, and power, it's a current into the voltage. So here how parameters we see, just you see this equivalent circuit of a PN junction. So depending upon the resistance of your device, across that a voltage is produced. This is your voltage, and the current flow through there across a load there. So this is how a device is represented. And if I say the 10% efficiency and looking at this curve, these are the important parameter. Whenever we go for measurement of any solar cell, we have to see the JSC, like it is short circuit current at 0 voltage. This is the maximum current, possible current, and the VOC, open circuit voltage, when there is a no current flowing. It means your device is not allowing current to flow, and it's a complete voltage there developed. So this is what your VOC, and if no resistance, the maximum current what is you are getting. So JSC and VOC are the important parameter for performance parameter of any solar cell, or even in the module case, the same thing happened. So here it is represented VOC 0.75 and ISC you can see. So JSC basically whatever current you are getting divided by area of the solar cell. So solar cell area is also important. That tells about the current density, the short circuit current density, and the fill factor. It also comes into picture. So what is fill factor? Fill factor is basically this is your area of the curve, right? And what maximum power you can draw from a device, it is at this point where my cursor is right now, this crossing point. It is a I max and the V max, this point. So basically, you know that in a solar panel, it is always we concerned about the power, ultimately what power we are going to get. So this is the load point where that much power you can drive from a device. So the area cover under this, basically this is a rectangular curve, maximum possible, and to that complete curve. So this is what it is your fill factor. So this area, this rectangular area over this curved area under this IV characteristic, it is a 0.706. Here it is calculated. So this is what the parameter is shown here for a typical solar cell device. Just to a few more thing about the same thing in a somewhat more representative form. If I say, so whatever I explained right now and different point, the P maximum, this is a maximum power is possible as defined, V max and the I max. Now the fill factor I max into V max by IC by OC, just I explained that, and so this comes into your for the efficiency of solar cell. All how the efficiency is Vm by Im by your power in. How much sunlight is falling on your device, whether it is a cell or the module. That is what that convert into the efficiency of a means your output by input. That is what it is. So from the IV characteristic, we can able to get what efficiency of any device is, but we should also know the area of your device because and also your this power, how much power you are applying there. Now, if I talk about the power, basically what is power? Input power, it is your sunlight. Though in the lab we work with the solar simulator, it is a simulated sun. But in the sun, from the sun, we get a light of different wavelength. It is a complete spectra starting from UV, for UV to for infrared. Things are there. But our solar cell will interact only depending upon the structure of that material. But it has a band gap. So that way we have to tune the things. Now, if I show you this is a typical curve. It is called AM 1.5, air mass 1.5, and this is a standard radiation for measurement of any solar cell, and we use a standard radiation. That is why we can compare our cell with other labs globally. So you can have a AM1, AM 1.5 or AM0. So how it is defined? It is defined AM by 1 cos theta. So just to make it more clear, if you see this figure, how it looks like. Let's say this is your earth and the surface. Over that you have an atmosphere. Now at the zenith, just whenever I am standing and perpendicular to my head, I said it is zenith and a light is coming from there, and at the top of atmosphere I say it is AM0, and at the surface of earth it is AM1, and at an angle of 48.2 this is called 1.5, right? We can do the measurement also at AM2, that is 60.1. So this is how it is defined, zenith angle. So one should measure because the standards say it has to be measured, solar cell has to be, or even the module has to be measured at AM 1.5, and this is what we use. And also we can do the intensity variation at different intensity. You see, you can have a different. This is for one sun or more than one sun. So one sun at 1.5, one sun is basically it is 1000 watt per meter square. Light is coming, we are converting into watt per square meter square. So 1000 watt or 100 milliwatt square. So normally what happen on an average on the earth surface we get 1064 watt per meter square. That is why it has been adopted in a STC condition. I will give you some detail about that also later. 1000 watt or the 100 milliwatt per centimeter square. The 1064 watt per meter square is the average solar cell intensity on the earth surface. So close to that 1000 watt per meter square it is adopted intensity of the light for measurement of any device, whether it is a cell or the module. With different intensity also one can say we measure. So when it is a 1000 watt per meter square, here it is given, it is called one sun. If it is half sun, it means intensity is reduced to half. If it is a quarter sun, intensity is reduced to 1/4, or intensity is doubled, so it is 2 sun. So this is how solar cells are measured, right? Now moving further, I will go something about our country and the different programs and how we are fitting into this, and then the measurement. Okay, so now I'm coming to some other part of my presentation. So you know that India has started a national solar mission program, and initially it was a target of 20 gigawatt by 2022, but later government has revised to 100 gigawatt by 22. Though we have not achieved that, but we were quite close to about 70 gigawatt, and now target is to 280 gigawatt of PV produced electricity by 2030. This is what the target set by Government of India. The nodal ministry is MNRE, Ministry of New and Renewable Energy. And in addition to that, government, our country is also a founder member of this International Solar Alliance. And starting with the France, our government has initiated this, and now there are 123 countries in this, and many more countries wants to enter into this club, International Solar Alliance. And initially these were the countries which comes under a topic of Cancer and the topic of Capricorn. The Kark Rekha and the Makar Rekha, you all know that those countries falling under this because they are blessed with the sun sign. God has given a more sunshine to these countries. So they are the members of this club. So this is, and now as on 31st August, just the last month, I have taken this data from Ministry of Power. Our country has a total installed power, including for all kind of power, coal-based, gas-based, nuclear, and hydro, bigger hydro. It's about 424 gigawatt. This is total installed capacity, and out of that, 131 gigawatt is the renewable energy. 31%. It's a great for our country, great achievement what we achieved. And out of this renewable, 71.61 gigawatt is only from the solar PV. So you can see 71 gigawatt. It's a huge. And among the river now we have crossed more than 50%. It is 54%, right? So this is what the status of as of last month. And out of total installed in our country, 94.82 is covered the silicon, and rest with other kind of technology. So material based technology, crystalline silicon, amorphous silicon, CIGS and CDT. And with here, if you see the cumulative capacity, I have given here up to December 22. I think it is a March 22 data, but now it is 71 in the August. So it's that 23 data is not here. So this is how it's all started in 10, and now we are here. It's beyond that. So in the last 10, 12 years, it's a huge achievement. And some more of the things I want to show you. Our country has made an impact. You know that now we have a solar park, solar power stations, a huge power stations in our country. One of the power station, normally it is called solar park, that is the Badla. It is the world largest solar park. We can feel proud in our country. Yes, we have the largest solar park in our country, and that is spread over a total area of 14,000 acres in Rajasthan, in the Jodhpur district. So it's a huge, and also the third largest is with our country. That spread over 13,000 square feet in the Karnataka Pavagada plant that is called, and the 10 plants of similar kind it is given here is the list. You can see starting from 252 to it's data is in the megawatt basically. It's more than 2.2 gigawatt. It's there 2000 all this. So if I say for our Delhi, because most of the time we spend our time, I'm talking about myself. Maybe most of you, many of you also. The peak requirement is 7,000 megawatt. So these are the plants. You see the capacity. You can imagine how much power just single plant producing power. Just to give you some feeling how much we have achieved in our country. When we got the independence in 1947, that time we were having only 1.3 gigawatt, that is 1362 megawatt. For complete India, I am talking about. This was our power capacity. Of course, that time it was coal. So these solar plants are much bigger than that what we are getting here. Some more glimpse for just I thought let me give you a scenario in the world scenario also. Some other plants with comparison to our plant, 5 best plant with other country. This data is little old in September 22. India has gained a lot, not much in other country except in the China. This is how far other countries. So India stand third, and sooner we will also cross other countries. Means Japan definitely in this PV installation, like we are expecting in our economics. And a total cumulative capacity of world, it is now 1185 gigawatt, and by 2050 it is expected 5000 gigawatt. So it is very important for achieving net zero. You know that India also want to have a 50% reduction in CO2 production by 2030, and by 2070 net zero. So all this development in our country and of course globally, it will make a good impact to our environment. A few more picture just to make it some interesting. Solar plant at Delhi Metro and the Cochin Airport. This was the first airport globally, I can say. It was completely the electricity given to this. Means all the operation of this airport was from this solar PV only, the Kochi Airport. This all good thing, but somehow you know that it has these solar panels have an end of life. 25 years normally it is given, but sometimes 20 to 25 years. And 80 when it is producing, the panels should produce at least 80% of its initial power. Then only it is rated. It can be useful, but with time is degraded. But in our country, what happened? This is the data given. Basically, a survey was done with measurement of the panel installed in our country. Uh, it's degrading fast. Normally, 1% degradation is considered to be good, but our country, those modules installed about a year or two ago, 2 years ago, I say, those are not of that good quality and they degraded very fast. The degradation rate of 2% annually, and it's a matter of concern. And this is why happened because we are not well equipped, having an accurate measurement or the quality checkup of the product in our country. And now MNRE has taken a drastic step, strengthen the things and made a protocols that will make a difference. And our country is gearing up for a quality installation. Or as such, you see for quality panel, it should is shown here. The degradation is less than 1%. This is the data of NREL. So this is what I wanted to show you, just to go further. And if it's degrade faster, it means what will happen? We'll have a more waste, means earlier than what it is expected if it is not of good quality. Here the quality infrastructure comes into picture. If your lifetime of a defined lifetime of a module is not there, if it is coming. So in a normal, yes, if it is completing its warranty period, then also you will have a waste. Otherwise, if faster degrade, in 10 to 15 years, you will have a waste. It's a huge loss, and also the environmental issue. Both will come there. Just to address this, I would like to show you one important data, global data, and also India is there, if you see. And that is somehow it is linked to national quality infrastructure. I say PV waste volume and the install. And two scenarios are given here. One scenario is that the first is uh, module is produced, installed with a warranty of, let's say, whatever defined, 25 years or 30 years. Sometimes 30 years also comes. So 30 years. This is projection is given for 30 years lifetime. So 30 years lifetime is there. So it means end of life of that panel is a normal life. If that normal life is not occurring, if modules are of not good quality, it means they are going to die, or the end of life will be declared earlier. So it means you will have a more waste. So this is what it is projected for 2016 it was there, and then 30 and the 50 projection is there, and it is given for first 5 countries: the China, US, Japan, India, and the Germany. And you see the gray curve and the black bars. This is about the volume of waste in the two conditions: the regular loss, the gray one, and the dark one, the black one, is the early loss. So early loss, it means you will have a more waste. If it is normal loss, you will have a lesser waste at a given point of the time. Now, so if I say, if you see the difference between these two, 48%, 25%, 15%, 66%, and here it is a negative somewhat. I have also discussed with PTV Germany about this data, but still we want to see how it is related with the quality infrastructure. So see, the Germany is well placed in solar cell. I can say they have a PTV, a very good infrastructure. They have a Fraunhofer lab. They all maintain with quality instruments and better uncertainty parameters with their measurement facilities. For India, it is a 66% it is coming. So whether it is a link with national quantity infrastructure, this I wanted to study, and I am in the process. Basically, we are in the process of seeing and I'm discussing with PTV Germany with this data. So yes, we can understand. Yes, the quality infrastructure is not that placed, good placed compared to the 4 countries what it was shown here, and we are also working towards that. And just to show you this thing, I have also highlighted in a PV magazine in just 21 that solar photovoltaic quality control is very much needed in our country. Otherwise, the waste management will be a concern for all of us. Further to this, just how this recycling will be needed. Basically, when see whatever done, it is done. It is over now. We have installed some of the poorer quality modules in our country, uh, and even if it is a quality module, after some time it will be declared as a waste. So we should be well equipped. We should have a technology to do the proper disposal of these modules with the suitable environmental friendly recycling process. And where now I feel yes, government is emphasizing MNRE and also the Ministry of Environment and Forest. They came with the gadget document also, and they included this thing into the electronic waste, and also set some protocol how one should uh, preserve these modules till a proper technology is there. By 2035, every producer or the installer has to preserve those modules unless they have a suitable infrastructure for recycling process. Further to this, now condition is that fast degradation of PV module in India and the step taken to quality check. So essentially, it is why it was happened. The heavily dependent on import of cells and module in our country. Module tested as per mostly European conditions, because our conditions are different than Europe. We have a harsh condition of temperature, relative humidity. Also, we have a dust and the wind in the Rajasthan area or in the coastal region. Wind is there. So in 2019, MNRE made it compulsory for manufacturer to obtain BIS certification for solar panels, modules, and inverters. So this is a good thing happened. It was not earlier. So I feel because of that, our installed module went into the faster degradation, more than 2% or so. And now things are changing with MNRE, and MNRE has taken recently in May also a scheme that is called ALMM, that has to be compiled with BIS standard. and they have identified 82 numbers of module manufacturer as per MNRE approved list. So basically now what module has to tell before production, they have to tell all the specification and so this is important. These are the, I was mentioning the gazette, just quickly going over there. And government policies and rules now it is coming into the place, recycling where also the standard needs to be made. NPL is also contributing in that how whether we can define a second life of solar cell. Now, so ultimately all this, now I will go some more towards the measurement, our primary standard and the secondary standard. But before that, I wanted to show you about this because as on date, this is much important for everyone, including our country, the PV circular economy and metrology needed at every step. See, starting from feedstock, what are the feedstock we are taking, ingot we are forming, wafering we are doing, solar cell we are making, module we are making, PV systems install, continuous monitoring is needed, and that monitoring devices has to be well calibrated. So all those things what we understand under the metrology umbrella, it is needed at each point, whether it is a material cell module, whatever it is, so that we can have a perfect thing what we feel. And this is what the second life of solar cell module standard need to be framed. Nowhere it is there in the outline, even no standard is there. I was discussing with the ISC personnel also one time. So if I present this as for the Indian PV quality infrastructure, it looks everything perfect. Yes, it is all there. We have all stakeholders there, and just it was missing for after the end of life solar panels. MNRE is there, and other regulatory means as a regulatory body. Power Ministry is there, and NPL is there as a metrology institute. We are developing primary standard solar cell. I'll show you some of my our work done there. And now as this CPCB and the Ministry of Environment, Forest and Climate Change, they also came into picture under this quality infrastructure, particularly the CPCB under this ministry to quality check the end of life module and it's regulate the process for proper disposal. So I feel now things looks quite satisfactory. In NPL, we have carried out some R&D work on recycling of waste module, and we have developed a technology for that. And recently, just on 19th of this month, this world leading PV magazine, they have appreciated our work also for ingots. Here also we take care of all metrological aspects. These are the ingots made, small ingots. We won't be able to make big ingots. We need a company for that we are looking for. So we all required resistivity and other thing with the impurity check. We do assess the parameters whether solar cell can be made with that or not. Similarly for thin film solar cell also, just all this. Okay. So now as for the fabrication and performance of solar cell, I'm not going to discuss about this fabrication as such. I think I have explained a little bit, and to this IV characteristic further. Yes, I think I have a few more slides for that. Anyway, yeah, I have a time I can cover. So as I mentioned, in the recombination losses, the back contact is the most important, where one can address how to minimize the losses, and most of the work in last 10 years or so took place in minimization of the losses at the back contact. About 50% losses were there in the solar cell, and so that you can improve the efficiency of solar cell and different as we understand that for any PN junction material is there, you can have a different kind of a losses. So this is, I'm just going fast here. And different technology schemes, improvement in the efficiency per part. Just I'm giving you a glimpse here. I'll devote more time towards our metrology aspect for the device. And other technology, it is called heterojunction with intrinsic thin cell. The best efficiency 26.7%. Basically, in the solar cell, from the outside we say it is solar cell, but those who are in the field, they know that number of things are there, and in the measurement also we need to take care of this, because like if I give the example, the contact we make, the shadow of contact should not be there whenever light is falling, otherwise uncertainty in our measurement will be more, error will be there. So that's it's all important. So technology, understanding of the technology, like for here you see it is for the tandem junction solar cell, perovskite and silicon based tandem. Two cells are there at the bottom, silicon, and at the top perovskite. The perovskite is a high band gap material and silicon is a lower band gap material, the 1.1 electron volt and it is 1.5 electron volt. So they are stacked one over other. So when light is falling over there, so it has to be ensured, yes, whatever light is going there and it's properly measured, the current generation is measured in this, and contact has to be properly made, and the inter contact here from one cell to other cell, that is also important. How normally in these cells the monolithic integrations are there, one over other, means small cells are there and they all cells are connected in series in a one pattern, I mean to say. This is how they are, but in a different way also it is there in the 4 terminal devices. So contact is very important when we are going for any solar cell measurement. Now some more things about our photovoltaic metrology activity at CSR NPL. We are developing this primary standard under a MNRE project in a collaboration with PTV Germany, with lowest uncertainty for reference solar cell of 0.35. And also we are working on organic and industrial silicon solar cell, reference solar cell, making of this we have initiated. Module test calibration we have started, yet we are not disseminating because in the calibration things we need lot of things there. Indigenous module test setup establishment, this is also we are doing. This is basically called the PID, potential induced degradation, for a country like ours. It's a very important test for a module. Synthesis of organic perovskite and other materials we do. PV related material testing, glass, silicon, extra, all these things we do. This is our R&D on silicon solar cell. We have made 6-inch by 6-inch silicon solar cell with 18% efficiency with latest contest concepts. The PERC solar cell with nano texturing in different configurations. Even thinning of the wafer we do with a smaller thickness, because this is what the technology is evolving with time. Lighter weight means lesser use of the material, and though as on technology is for 180 micron, and we are working with the 50 micron, so 1/3 thickness of the silicon will be needed, and this becomes flexible up to certain extent when it is go with the thinner. So Fraunhofer Germany is also working in that. In the emerging PV, NPL is also working for the perovskite solar cell, organic solar cell, on low cost heterojunction solar cell. This is also our new initiative. It will be a cost effective process because the conventional silicon solar cell technology is a high temperature process. At least 900 degree Celsius temperature is needed for the diffusion, so that you can have a junction in the device. But this heterojunction concept is a low temperature process, and particularly with the organic and inorganic all room temperature process. Now, as for the primary reference solar cell, this is our facility. We are developing in collaboration of PTV Germany, and it's a huge facility. It means a lot of components are there, and it is a laser based. See, the sunlight. You know, the that is the important in primary reference. I mean to say why it is a primary. Basically, for any solar cell measurement, essentially the most important point is your light, the sunlight. The sunlight or the simulated light, the light you are using in your lab or at the measurement table, that has to be well calibrated. And this thing is calibrated with cryogenic radiometer. And for light, you can have a lamp. Lamp can be have a different kind of a functional lamp or xenon lamp. Normally, xenon lamp gives a good spectra which matches with the solar radiation. And later, in recent past, LED based lamps came, and now this is a laser based lamp. And we will be the second after the PTV using the laser based for our standard things. And though it is not commercially available in any solar simulator, the commercially solar simulator laser is not being used. Why we preferred laser to narrow down our uncertainty, to lower down our uncertainty. I'll show you some data and how we do the measurements. In the laser, the bandwidth is lower. What bandwidth means, okay, whenever you define a light, let's say if I define 540 nanometer, so 540 nanometer plus minus how much? Whether it is a delta function with narrow bandwidth, lower bandwidth. If you take a halogen lamp, similar kind of a lamp, or this xenon lamp, the bandwidth is more. In the case of LED, up to certain extent you can minimize the bandwidth, but in the laser basically the spectra is looks like a delta function with narrow band, so that gives more certainty to your spectra. Like if I am trying to measure generation of electron hole carriers in my device at 540 nanometer, so precisely it is very close to 5 nanometer plus minus very minimum deviation. But in the case of LED and the lamp, it is more. So that is why laser is important. So here the spectra is shown. So a photograph is shown for our setup. And if I go with the schematic of that, uh, basically it's this all setup for the laser. You can produce different wavelengths there, and then you have a chopper pulse to CW, continuous wave converter, and the optical wire. Then through the monochromator, your light can fall on the solar cell. And also we give a bias light so that we can minimize the effect of other parameters there. And whatever the light coming from your monochromator given by your laser will measure the generation of current there. And this the setup which we are going to have, it is already developed there. Very soon it will be operational in NPL. It is 0.35 uncertainty for 20 by 20 millimeter of solar cell. And if it is an industrial solar cell 156 by 156 mm, then it is 0.6%. This is how it is going to be useful for our country. And laser alignment is very important there. Some closer look of that setup. If you see that the laser light is coming and all the components there, it is targeted at 480 nanometer at this time when this photograph was taken. And this is your chopper. The light is all coming through chopper. So chopping the frequency is important so that you can know exactly at what frequency it is falling at the solar cell. And in the feedback loop, you can know, yes, this is the wavelength which is falling on the solar surface, and you are getting current out of that. So this is how it is. Optical chopper, it is this chopper. So when it is in operation, this figure gives that. If I move further about the bias light, this is the bias lamps arrangement there, and 80 lamps are used. Basically here a array of lamps are there. So depending upon how much intensity you want and the uniformity over there, you can at uniformity over area and the intensity over area. Accordingly, you can choose the number of lamps with its power. So this is called the biased lamp in the facility, and this curve shows the uniformity in the power there. So non-uniformity we have measured here. One example, it's given for 500 nanometer wavelength with the 0.2% non-uniformity. And my two colleagues from NPL, Dr. Pratap Pati and Dr. Sanjay Kumar Srivastava, they went PTV Germany. They spent 4 months there to have the knowledge transfer and be part of the system development besides the assessment of the system performance. Sanjay and the Pratap is there. I have also seen the system operating there in last October. Now, if I further talk about what are the things involved there in this PV calibration chain, it is basically the cryogenic resonator. The light, you know that the light, sunlight I say, or the simulator light has to be measured properly. Yes, what wavelength it is there and how much intensity is there. It has to be calibrated with against some detector. And for primary standard, ultimately you have to have a detector which does not give a signal from any other source. Means there should not be any thermal energy, because you know that all detectors are semiconductor materials. Essentially, it's a PN junction, photo detectors, like it's a PN junction. But if there is any thermal energy, even at room temperature, you get some thermally generated current there, electron there, and which contribute to current. So this is a source of error. So that is why you need a cryogenic radiometer. Radiometer is just, you can have a spectra of light, and cryogenic, it has to be measured at cryogenic temperature, absolute cryogenic temperature, lower temperature. And that is why there is no contribution of any other source for generation of the current except the light you are allowing to fall on the surface of the cryogenic radiometer. And this way we are precisely knowing, yes, this is how we have selected this wavelength with having this intensity, or we are getting this much energy out of that. And so this is go to the standard detector, and then you have a reference solar cell and your PV module. So this is how the traceability is made for a module. And so this is how we have done in our case for creation of this our primary standard facility. So it is calibrated against cryogenic radiometer. So right now in NPL we don't have cryogenic radiometer. We take the help of PTV in this case, because it's a very costly infrastructure. Though our optical standard earlier was trying to set up this, but somehow it could not be managed so far. But we intend to have this facility also with our optical standard, because in the photovoltaic will take help only from our optical standard, then only it will be possible to get it calibrated at NPL, our primary standard facility. Otherwise, till then we will take the help of PTV Germany. Further, if I go, so with our setup at PTV, when it was made, we went with the international intercomparison involving 3 labs and the 4 setup. 2 setups were in the PTV, one in the NREL, and how it is. If you see, if I have given a schedule for that. For two cell, crystalline silicon solar cell, the name is given RS32 and other is 072016. One is a non-linear silicon solar cell and another is a linear solar cell, and it is measured 4 times at different places like PTV Germany one with their old system. Then it went to NREL. Then again it is measured at PTV Germany and then in the NPL system. So this is, I'll show you the data there. So this way we went through the assessment performance of the system I described just now through round robin intercomparison, and this is as for WPVS standard reference solar cell. Yeah, so some of the data calibration value for the comparison, it is for the spectra, and there the power curve is given, and this is measured at 4 times, the 1A, 2, 1B and 3 is what it is given there, and earlier it was described for this RS32 silicon detector. So this red is the value with the uncertainty values, 4 places. So it falls under this dotted line. So it's quite good in that sense. And if I present this thing, if you see the international status of NPL India, it's a best, yes, with the 0.35 uncertainty, I can say. The PTV Germany, though they have helped us in making of this system at their place, and in their system, as of date, they have a 0.4 uncertainty. Our system is better than them, their system. And in AICT, it is 0.72 Japan. In NREL, it is 0.9, and in TIPS China, it is 1%. So if I locate at these 4 places, you can see there are other centers also, renowned center, JRC Italy, BSNG Israel, and in the Spain also. But in future, we plan to have one more round robin with this, what we did earlier. So this is a flow chart in NPL what we are doing. You can understand what's our plan. Traceability through unbroken chain. So essentially, normally you know that in any solar cell, we get the reference solar cell and mainly made from the NREL. Though PTV also gives that a standard reference solar cell has to be there. In NPL, we have a NREL solar cell. The primary facility still it is not operational. From we are expecting from April 24 it will be operational and we will disseminate our services. But till now, what we are doing, we have a secondary standard facility and we maintain traceability through reference solar cell procured from NREL. That is called a standard reference solar cell. And we have a class AAA simulator. I'll define you class AAA solar simulator. So, and whether industry also does the same thing. So industry can approach us. Normally, for few industry we did, but mainly our focus was the laboratory systems. You know that in our country more than 300 groups, researchers working on different kind of the solar cells. So they also approach us for just for the measurements. They don't look for the calibration certificate, but if they want, we can give that also. And like CL and others, some industries we measure their cells in our facility. And this way we maintain our standard, this traceability. Once we will have a operational our primary reference solar cell, we will not go with the NREL cell. Our reference solar cell, what we have, we will calibrate against our facility, primary reference solar facility. Okay. There is another approach we adopted, that is still we have this in our operation. Our solar simulator, you know, there are various components. I'll show you some of the data. And we calibrated our solar simulator component wise. And finally, we calculated the uncertainty budget of that. and we get calibrated with our apex facility. Presently what we have there, like calibration of lamp, current voltage meter, temperature sensor, all it is that. So this is I have shown you this the blue one usually followed. Okay, we also follow, but since we have this, we are privileged. We are in NPL, and we can easily assess the apex facility of our NPL. So this we prefer, and we do this. We get calibrated our things with our NPL apex facility, and in future we'll go with this our primary reference solar cell starting from next year. So this is how traceability chain is maintained in our case, and this is how the things is there. If you see efficiency of the solar cell, I also presented earlier. I said four parameter, and it has to be measured at 25 degrees C, precisely 25 degrees C. This is what the requirement, the condition is there. To fulfill this, means we'll have a well-defined optical input, current, meter, voltage source, measurement is required, area of this cell is required, then temperature sensor means it is sensing properly. If it is 25 degrees, how much uncertainty in that plus minus value. So in our setup, the second is standard setup. So we have a xenon lamp and we get it calibrated. So basically this is what I wanted to show you. I was explaining without any slide curve, but here you can understand like if I focus at this wavelength, so you can have this kind of a blue kind of a spectra, or you can have this kind of a spectra. So in one case you can with the laser or LED. So basically this is what the bandwidth. So here you will uncertainty will be more. If you say yeah, this is my wavelength, but other spectra is also coming there of different wavelengths. But if you are saying yeah, this is my wavelength under this curve what it is shown, you have a lesser error in that involved. And in the case of laser, this is more quite close to correct one, lesser error. That is why we are getting 0.35 uncertainty in that. And so our laser spectra is calibrated against prior radiometry. So this is our upcoming primary calibration facility. If I talk about the crystalline and thin film, what are the standards there? Like total standards, 10 standards are there, and 9 is 6094 series and 60891. So these 10 standards are as far as cells. I'm talking about the cell, not for the model. So these are the standards for the light source, for the reference devices, for the PV test devices, and this is what you get in terms of IV characteristic. Yes, so this is your power curve. The black one is the power curve, and your green one is your IV current and voltage. So this has to be measured with this standard IV curve. This is how defined, and other components there are. I'm not going deeper in that. What are these standards? As such, it is available in a standard document, even in the IS standard also they are described. And for the STC condition, just three important things are there, as I was little bit explained earlier also. So if this is your standard curve, I as AM 1.5 I was mentioning, as for the IEC or this global standard or GSM standard, the different curves are given. So air mass 1.5 spectrum, that is called AM 1.5, that has to be there with matching how much it is matching this spectra, how much it is matching. Then intensity of the spectra, total spectra, integrated spectra of this one sun illumination, that what I earlier defined, the 1000 watt per meter square, and the cell temperature should be 25 degrees C, and this comes under 609043. So procedure is there. Okay. So for any solar simulator, so now so all these things comes into a solar simulator, and the solar simulator can be classified as AAA, 3A or ABC or ACC, whatever it is, basically. Normally the best solar simulator is AAA, AAA, or sometimes now it is A plus is also called. It is defined for all the parameter, like you see the spectral match of all. The matching is very important with three standards here it is given, ASTM, IEC or JIC. So in this case, normally in NPL we adopt this IEC standard. Now it's also Indian version is there, IS. So ABC, and so in this case, like the matching, if I say matching is plus minus 25%, it means 0.75 to 1.5. So if I say the solar spectra, like here, I was presenting at a particular wavelength, if this is the intensity of spectra, so how much it can go up and down. So it is allowed 25% only. So this is what it means. So if that is within this limit, it is called A. If it is not in that, it means if it is a 40%, 0.6 to 1.4, then it is B. Otherwise, it is C. If it is more than that, 60%. So definitely, this is a advanced version, more precise version, more accurate version. Now, another thing is non-uniformity of total irradiance. Whatever the light falling on your test sample, uniformity is quite important. So if it is within plus minus 2%, then it comes under A. Otherwise, within 3B or more than 10%, lesser than 10%, I mean to say, it is class C. Non-uniformity in total irradiance for large area, for a small area it is defined. Total number of test points, how much point I am taking. Let's say if I am having a 300 millimeter by 300 millimeter, on that I am measuring at 64 location. See, this is why I am considering the best standard, IEC standard, because here you are measuring uniformity in a better way. You have a 64 point. In this case, this standard says only 17 point. Here it says 36 point. Here you see 64 points. So we have adopted this, of course, and 64 points measured different location, and then we contribution of that into the total uncertainty factor, so that you can estimate the uncertainty in your measurement. Then short temporal and the long temporal, about the when intensity of light is falling on that, how much it is allowed there in the class A, class B, class C. So this is how it is there in any solar simulator. So short term related to data of the sampling time, how much you have given a certain time, and out of that time how much data you are collecting. Long time related to time period of IV measurement, how much time you are giving for that. So this is about the description of solar simulator in different class. And further, the solar simulator, what solar simulator we are using, other instrument there, and the measurement procedure, reference device what you are using, test cell what is there, and then you have to data analyze so that you can do the uncertainty measurement of it. For emerging technology as such, no standard is developed, but we have adopted some protocol, and also we have published that into articles, how to adopt the procedure. I'll give you the reference for that for cells. Now I talk some, yes. These are the facilities we have: optically radius, current measurement, voltage, dimension, and the temperature. So using this, our expertise and the facility available, we calibrated our solar simulator. As I mentioned you, there are 2-3 ways. Means with the reference solar cell also you can go. We'll go with our primary reference measurement facility, and this is what presently we have. We have adopted our facility. So these two solar simulators we have as a secondary reference. One we use for industrial silicon solar cell, and the second is for the thin film solar cell, mainly for organic and perovskite. Nowadays we are getting cell, and it can measure 100 mm by 100 mm. As such, we have the facility, but hardly any lab approaches. They just approach us for the measurement, not for the certificate, because they need it for their academic interest. So protocol about this instrument, we have presented our data in this publication. If anyone is interested, publication I can supply. As such, it is online available. And this is how different capabilities we have, uncertainty in the measurement uncertainty at NPL, and that we adopted to calibrate our these two systems which we have as a secondary reference solar cells given here. These are the various one example for thin film solar cell. Various components like optical irradiance is come from the Xenon lamp. It is of Aisho Japan. Photo intensity power reference photodiodes we use. Reference solar cell also we use. Current voltage we have a Kifle source. So it's basically the current meter and the voltage source. Two PID temperature sensors are there, and the area we measure. That for the area we use aperture. I'll show you how we do. And with the calibration, basically we obtain our from the OPEX facility all the data, and on the basis of that we calculate uncertainty. It's all standard practice for any kind of uncertainty calculation. We also adopt the same equation involving all the parameters type A and type B there, and we do the uncertainty calculation. Here a few measurement data I'm showing you for a reference solar cell. This is a reference solar cell, and we recorded 12 number of times this reading, different parameters, the current and the voltage, the power and the fill factor, what the parameters I was showing you, and the efficiencies parameters different. And you see the solar cell parameters for original value. This is given to us by the, and we measured it here. This quite comparable. You can see our measurement facility is up to the mark. This is given by NREL. So we have measured it here in our lab. Even the laboratory cell, the organic solar cell, we do the measurement, and these are various reading. You know, the organic solar cell are not that stable. That is why some instability is visible here in the measurement because of that. This is, I feel it is not instability in our measurement. It is a material characteristic. The material is not that stable because of that fluctuation in our data it is coming, and we have measured this uncertainty value with the efficiency of the cell. This is just I'm typically giving you some of the work we carry out at NPL, some glimpse. We also do the spectral response. So two things are there. One is the data I showed you there. It is a full light. You say the from the solar simulator after the filter AM 1.5, whatever falling on the surface of a device, test device, that is our reference solar cell or the organic solar cell. Two that I have presented you here, the reference solar cell and the organic solar cell, that get measured, a light, complete light on that. Okay, and out of that current produced. Another is the spectral response, which means each wavelength of the solar simulator, the light source you can take, and whatever the current is produced there, you can measure it here. How this is what it is shown here. So this is how it is measured. So we have for our organic solar cell, you see we have measured it, and also for the reference organic solar cell, reference solar cell, and then we fit the parameter into that, and we estimated the things, internal quantum efficiency. So ultimately, say if the 17% efficiency of solar cell is there, so in the both way it should come, ideally it should come same. The current produced, I mean to say, means the whole spectra at a time or the individual spectra of that when it is going there on the surface of the cell and contributing to current and the measure it, the integration of that. This is what the spectral response is that. When we integrate it, the current density, like here it is given 32.85 and here it is 33.6. So this is a procedure, one should adopt it with the spectral response solar cell. It is not if you are measured with one go with the sunlight. If you are producing with a spectra, that is always good. Normally in the protocol, even in the standard for industrial modules, it is not given there. It is with the pulse light, it is measured the power in terms of current and the voltage. So what does it mean? It means what I'm explaining right now. One can do this way, just involving step 1, 2, and 3. This is just you have a light, means you are inspecting the area and the other measurement, and finally you are measuring only the IV characteristic. But before IV characteristic, you also, if you are measuring a spectral response of that with the linearity check, so this will give you more accurate. Uncertainty will be better in this, your measurement uncertainty. So this is what one should adopt. Our instruments are in the clean room, ISO 7, but presently, but now we have doing it's an old slide actually. I've shown this data height for the spectral response. I think, yeah, it's my old slide. I will somehow taken it here. I should have corrected it. The common source of error now, improper calibration of solar simulator. That is the one thing, whatever I was mentioning you. Non-uniformity in optical irradiation, measurement error, measurement in your current and voltage, source temperature. Area of solar cell, it is very, very important. And mostly it is important for a smaller solar cell. Those who do in labs, they always do the mistake with the calculation of the area because their cells are very small. And this is the uncertainty in device measurement may lead to ambiguity in the product value assessment. We all know that it has an implication, technical and the financial term. So it's important to minimize this error as much as possible. Or if error is there, you should measure it and mention it. That is what. Just I'm giving you one example for area of the solar cell device we carried out in our lab. We have taken different cells. These are all different cells, but different cell from different persons or different cells are there and having very small areas. So you see, when they have given a area of the cell and we have measured it, actual measure it, so there is a difference, the blue and the green, blue and the green. So this is what normally mistake occurs in measuring of the area and finally the measurement of the efficiency of the solar cell. So area is a very critical there for a smaller size mainly. Yeah, this is some of the devices we measured for dye-synthesized solar cell, and there we observe, yeah, with the area the efficiency is reducing. That I also mentioned, as you go with the module, the efficiency of the device reduced. So uncertainty in our measurement of area is this much. So with different apertures, we have a calibrated aperture. We perform the efficiency measurement of this dye-synthesized solar cells. This is the same thing, I think. Yeah. So in the case of test for the module, normally this is what the standard is, IEC 61215 or 61646. There one has to diagnose this module, visually inspection for, and the hotspot, then you have an electrical measurement in the performance parameters, thermal, irradiance, environmental, mechanical. For the thin film, light soaking is also done. And in the safety, this is also given. Yes, one should go for this electrical, thermal, and the mechanical. And for the PID, as per 62804, we have also developed some test facility for PID in NPL. And for the safety standard, this is all given here. So one should be aware of this for module testing. In NPL, we don't perform all these tests, but nice, some of you may be knowing, National Institute of Solar Energy is the autonomous lab of MNRE, situated in Gurugram at Gwal So they have most of the facility, and few they are also developing, but it's not the primary standard facility. But in NPL, we want a calibration facility for module only for the STC condition. And these are all basically the most of the parameters are for the derived unit. The performance are estimated. Yeah, this is the result I'm showing for our facility, potential induced degradation. It is important because whenever in the cell the high current moves, and then in the module in the uh, power line, so large power result into a generation of heat, and and it harms to your other component with encapsulant and other things. So it's important, particularly for our like country, the heating effect and under the high flow of the current. So that's why it is now integrated. Earlier it was not that, if I say rightly, but now it is incorporated in our Indian standard, IES this standard. Just quickly, I think this I have shown, right? Maybe little bit about those, just for the sake of what are these standard. Is defined here for light source measurement and principle for terrestrial photovoltaic and other things. ISA 6094 standard for ABC, like I was mentioning for solar simulator, in what are the conditions there, for the reference device, what are the applicable ISA standard there, and some remarks are here given how one should use it. Even for the test of reference device, IEC 60904 5 for the determination of equivalent cell temperature and other things, measurement of spectral response or the method of linearity measurement and procedures, what should be followed, that is given here. Further continuation of that for light source of PV devices, these are the standards given. How to measure IV curve, only one has to measure that. There is also, one should follow this standard. The standard method for that is the STC condition, standard method for measurement of IV curve, depending upon the light source, natural or the simulator. If you are measuring in a open air, means under the sunlight, natural sunlight, or in a simulated lights, then how one should proceed. Steady state or the pulse, as I was mentioning, the pulse case. How to translate IV curve under this IEC 6089, procedure for temperature and irradiance correction to be measured, and from experimental to targeted. So these are the standards for measuring of a models. And for other some environmental tests, PV module durability test, that is additional environmental test is also performed, like salt mist corrosion testing, like for coastal region it is very important. Ammonia corrosion testing also again important for that. Dust and sand testing, potential induced degradation, this is what I was mentioning. Dynamic mechanical load with bearing load. How your, what is the mechanical strength of the module? The glass, glass is there, and it should have a sufficient mechanically strong, so that whenever there is a, what is called, वो ओले वृष्टि होती है during the rain time, from that it should be avoided. So one should have that strong enough, that module. So this load is very important. Dynamic mechanical load testing, fire testing, flammability testing, then highly accelerated states testing, outdoor performance comparison measurements. So these are some additional tests are there. So it has to be. So with this, I think I am with time. I try to manage with time. So I can make a conclusion. Whatever so far I addressed, mentioned about that, with rapid development of low cost and high performance silicon solar cell module, the solar PV market is expected to boom further in coming years. The solar PV installation is encouraging and could make its renewable energy more affordable. In view of this, a strong meteorological infrastructure for solar PV is major challenge and need to strengthen. I'm talking means everywhere, because we are going for installation and installation, but all modules, whatever. See, normally we go with the batch test. Out of 1,000 module, this number of modules should be tested. Protocols all there. But if you are going with the modules in our particular country, there are few facility for module testing available. So that needs to be enhanced. Then only we can ensure the quality of the module. So this is what I try to making my point in the first point. Second, the standard needs to develop to define second life of material, because I emphasize there, this is my heart to my area, core, my area, that is recycling of that. The second life is important, because we should not throw it, we should not uh, declare it that it is life is ended, because as per the definition it is 80% operational life, but still it has a 80% of power, one can use it. If not to the grid connected, maybe for lighter application one can use it. So for that quality infrastructure need to be developed, specification needs to be developed, standards need to be developed. This is what I mean to say. In India, the research on solar cell is being pursued in various scientific laboratories and industries. However, there is no facility for validation of solar cell efficiency. Though we have a secondary standard facility, but I'm talking about more strength and technology and facility. So CSR NPL has taken up an initiative for setting up a national facility for validation of solar cell with maximum possible accuracy. It's about primary facility. So primary calibration facility of solar cell efficiency is being established at CSR NPL with the world best efficiency and certainty. So I'm hopeful that it will be disseminated from next year, April 24. If we go with our schedule. And at the end, I would like to acknowledge uh, Director NPL and all members of PV Metrology Group, specifically Dr. Pratap and Dr. Sanjay, and MNRE for financial support, for particularly for primary standard. But MNRE has also MNRE even at BST, I can say, they have financially supported us for many of our activities, particularly for doing R&D for solar cell, and in recent this MNRE financial support for primary reference solar cell. And the PTB, they are supporting us for the development of primary reference solar cell measurement facility. So with this, I thank you all for kind attention and listening me, and I'll be happy to answer your queries, if any. Thank you very much.
Thank you. Thank you very much, sir. Your presentation was an eye-opener. It is one of the best presentation we have seen. And I just observe that it is a very new and the interesting topic, interesting subject, where a lot of work has to be done. What are the most important point? The efficiency, over which we have to work, how to test, how much efficiency after a year or so. Then only we will be in a position that how much KVP we are actually getting, which was installed from a solar cell, let's say about 2 years back or 5 years back. What is its efficiency today? So these are very important topics. Secondly, how the environmental conditions are affecting are solar cells for generating energy. So all these factors are very important. Certainly, sir, you have actually enlightened us on this topic. I would like to thank you, sir, for this wonderful presentation. And then we have large number of our friends. Santosh ji, will you take some photographs so that we can put it on our Twitter handle and other?
Okay, sir. Okay, sir.
Please.
Thank
And
you.
sir,
Thank
with
you
your
very
kind
much.
permission, with your kind permission, we will put this presentation as well as your this today's video on our channels as well as YouTube channel, Facebook, etc., so that the participants can see at any point of time.
Yeah, nice.
Thank you, sir. With this, I would like to thank all the participants, our Honorable Dikshit Saab, my friend from Nigeria and other countries. Thank you very much for participating in this workshop. We will meet again in the next week. Santoshi, can we close it?
Okay, sir.
Thank you. Thank you very much. Next week we'll meet. Thank you.
Thank you. Thank you.